It's fantastic to have you here and have a chat with our community. Let's start kind of in the first third of this chat, a little bit about the early days, of which you were professor at Columbia, correct?
True.
And then joined the NASA Jet Propulsion Laboratory. Tell us a little bit about, what was your mission when you joined there, and a little bit of kind of behind the scenes stories.
Sure. So the NASA Jet Propulsion Laboratory, which is part of Caltech, out in Pasadena, builds all the robotic exploration vehicles for our country and other countries sometimes. So Mars rover, for example, is one of those things. And my mission out there was, because I was working on CCD technology, was to help with space technology in the area of CCDs and camera systems. And I always wanted to work for the space program, and this was like an opportunity.
Was that always? I mean, for what
always,
age?
Always.
When did you get that into?
Well, I was born like right at the same time as Sputnik went up. So
Okay.
I would say right from there.
That's great. And obviously delivering on the goal of joining them. That must have been a fascinating. So how was what was the team like? What were you guys focused on building at the kind of the first onset when you joined?
Yeah, we were dealing with the problems with CCDs in space. CCDs work great for many things. I always like to say that there are two things that amaze me that work in life, in engineering, and one is that those big jumbo jets could fly,
They still amaze me, especially when I'm sitting in them.
Right, and the other was that CCDs can work also.
Can you give us one sentence to the audience? Most know, but one sentence define a CCD.
So a CCD is a charge-coupled device. It was invented at Bell Labs in 1969, and was the mainstream solid-state image sensor technology for many years.
Okay, and then evolve a little bit forward. You kind of said, okay, you're working with CCD, and what was the moment or kind of process in saying, hey, this is not going to work for us as a better way?
Right. Well, first of all, looking at the problems that CCDs have in space, which is like they get exposed to radiation and the ability to transfer charge deteriorates and a few other things, bad things happen. I thought, well, if we don't have to transfer charge very far, that would be a useful improvement and help avoid these problems. But the second most important thing that happened, or maybe the first most, is that the NASA administrator decided that we needed to be faster, better, and cheaper in our spacecraft. And that pathway included miniaturizing everything.
Right.
And so that flowed down to my group as miniaturizing the cameras. So how can we build a camera that's bigger than a refrigerator at that time on spacecraft and make it much smaller, maybe shoebox size, or, I mean, it doesn't seem very ambitious, but that was would be a big change.
Big change from the toaster to the shoebox.
That's right.
And so, I mean, some people, when they're asked to do that in different companies, they either say, no, that's crazy, that won't work, or I can't wait to figure out the way to make it. So where were you and your team at? I'm sure in a bunch was everybody on board, we can do this? Or what was the behind the scenes? Because, as you know, there's a lot of entrepreneurs in the audience that frequently they're trying to do things where people say you can't do that. And I always like investing in people that, no is not in their vocabulary. It's not now, or how do we, go about looking at solving a problem?
Well, I think most technology, you kind of go through this period of technology push versus technology pull. And at first you have this new invention or thing, you're thinking, oh, this is really cool, but I wonder what it's good for. And then you have to figure out what the market is, and you try to turn that into market pull down the road.
Right.
So having the NASA administrator say, hey, we're going to build these faster, better, cheaper spacecraft, make them smaller, all of a sudden these ideas I was thinking about for making CCDs work better, suddenly it turned to pull from the head of NASA. It was like, we can use this technology and make it happen. So that really infused our group with a lot of anticipation and excitement.
Fantastic. So tell us a little bit of kind of on a very kind of high level bird's eye view, the timing, was it, obviously it wasn't days, I mean, it was years, and, in the early, at the laboratory, what were some of the aha moments in there and how roughly kind of the timeline to kind of realize those progress?
I should say that CCDs are very complicated to operate and very hard to build electronics. So if you ever had to test one, it's like a lot of screwing around with things and adjusting things to get them to work right. And there's only a few people on the planet that really knew how to make cameras using CCDs anyway. So an aha moment for us was that we built our first sensor, we plugged it in, and it worked right away with no adjustment. And it was like, oh,
what year was that?
Work.
That's great.
Yeah, this was like 1992 or 1993.
Did you take a photograph?
Yeah, we did, actually. Took a picture of the picture.
Okay, good.
We took with
Just checking, because obviously that's kind of...
It was at least 1,000 pixels in total.
That's fantastic. Okay, and so that was one aha moment. And then, so, kind of thinking about, at that point, you were trying to push the limits and then start validating this new technology. So what were a couple of the kind of big steps that you said, okay, if it does this, then we're on the right track, or if it does this, and did they do those things that you expected?
Yeah, so of course our goal was to build a sensor that could be integrated with a lot of other electronics, a camera on a chip. So first we just built the pixels to make sure that they worked, and they gave pretty good optoelectronic performance. But then we had to integrate other things on the chip, like the analog to digital converter, which right now everybody thinks that's pretty obvious, that you want to have the conversion to digital right there on the chip. But I actually went to Japan for a tour of Japanese companies and asked them all about, why don't you, what about ADD converter on the chip? And they all said, oh, bad idea. And they had some reasonable reasons for it, but the attitude was that you shouldn't be doing this. So integrating the ADD converter on the chip was a big deal at the time, and then integrating the rest of the camera electronics also became milestones, if you will, in the development. And then it became pretty clear that this was going to work, and it worked.
To you or to those companies that were saying it'll never work?
Well, that came later.
Right.
So
to you internally?
Yeah, to me internally, and actually to inside our group, and so that sphere kind of grew slowly over time. There were a lot of people in my technical community, CCD community, that said it was a bad idea. We should never do this. And then one by one, like dominoes, they kind of switched their position. Was there one major, and that's that part of your career and working on the CMOS invention, that was the biggest milestone that helped others understand that this is really going to happen? Yeah, I think when we started working with companies like Kodak and National Semi, that all of a sudden it became more real and got credibility. And probably the most important thing that really flipped a lot of people was Toshiba decided to go into this.
What year was that? So that's we're jumping ahead a little later.
Yeah. So that's later in the 90s.
Okay. And so what's interesting, so let's step up, wait a second before we get into those. I mean, so in the days before Kodak and that validation, I was working on a similar kind of, in the imaging space in Silicon Valley at Home Network. And we said, we're going to build the first broadband photo community on the internet, 96. And it sounds like something similar happened in a different spectrum, obviously, of the imaging industry. You were on the sensor side, and we were on the end user community side, of which we went to Kodak and Nikon and all the camera companies. And especially at Kodak, I might have told the story to some of you, but we met, three of us from Silicon Valley show up in Rochester, and they walk us to a tiny little room to have this internet imaging meeting. No windows. We're with two people that are, mid-level, that they're supposedly in charge of the internet. And we went this hour-long presentation, and then I said, so we don't think we need an internet imaging strategy. And I'm not sure what you're saying is really going to happen. I think you had similar discussions with some of the big players.
Well, but it also evolved over time. And I have to say that, it's true that experience, Steve Sasson is a good friend of mine, by the way. He had a miserable experience early on. When we went to the engineering guys at Kodak, they were interested. They were very interested.
Okay.
And then the problem kind of started
that makes sense.
Fire up the
So
chip.
the business folks and the marketing folks and everybody that was making all the money on the film.
That's right.
The big turning point with Kodak in the wrong direction was when they realized that film sales went down for the first time years later. And they knew that digital was going to happen.
Yeah, I think the problem with Kodak is they didn't realize that they were an imaging company. They thought they were a chemical company.
I agree. Absolutely. Okay, so, and now at that stage where you started realizing, at what point did you decide and why to create a new company, which was Photobit, right? Which was that technology. So at what stage, and there's many researchers in the audience that, they're working on projects, maybe not at the Jet Propulsion Laboratory, or maybe, and they're at universities, and they say, well, should we commercialize this or not? Or do we want to do it or not?
Right.
So why did what was the behind the scenes thinking process and decision process?
Do you want the The story or the real story?
I want the real story.
Oh.
You knew I was going to say that. I want the real, behind the scenes,
Yeah.
nail biting, if that was the case.
Well, first of all, I was very frustrated because I went around and tried to get a lot of U.S. companies to get interested in this technology.
Right.
And they all were blasé about it. And, the Japanese controlled the CCD market by that time, and it's like, let's get in there. We can do this. You can do this. And they were mostly uninterested. And finally, I was just frustrated. And then at the same time, now she's my ex-wife, my wife at the time, Sabrina Kemeny, was home on maternity leave, and she was also an engineer, worked with my group. And we were like, you could buy a little CAD system at home and design chips, for people that we're starting to get a lot of inquiries about this new technology. So she did, and so my day job was at JPL, and she was in the basement of our house, and then things really picked up after that. I mean, like with people showing up at our house after I left for work, these guys would show up at our house and go into the house, and then they would leave, and I'd come home, and it's pretty bizarre, I think.
And so how did you separate you're working at JPL and, and also the tech was not the same. I mean, it's similar. I mean, how did you deal with IP?
Oh, yeah.
So the behind the scenes of that.
Caltech owns still to this day owns the intellectual property.
Okay.
So Sabrina went out and actually licensed that technology from Caltech, which, believe it or not, was the first time they ever licensed technology that was invented by JPL engineers to the JPL engineers. That's 5,000 engineers at JPL.
Really?
Yeah, they were afraid. They were afraid that somehow we're getting an inside track or something.
Okay.
But I think anybody who's gone through technology innovation knows that, it's all about the people, and who best to commercialize the technology than the fathers and mothers of that technology.
Got it.
It was so it was born out of frustration, and then after it was successful, everybody was talking about how Caltech successfully spun off this company and things. But actually, Caltech was pretty good. JPL, they weren't quite so happy when I started hiring my former group members into the company.
Were you still working at JPL then? At what point did
there was a while.
Like they're going to send you, okay, enough.
Yeah, so there was a while before I left, a couple engineers left, and then after I left, there was more came, and then finally said, please don't do that anymore. And we said, okay. And we lived up to that.
And at what point did you leave full-time to go full-time into?
It was about a year after the company was started. So.
Okay.
And actually, you come to a realization at some point that, like, wow, if this company is going to succeed, we need all hands on deck. And I would regret terribly if I didn't put my all into it, and this company failed. So that's when we decided to take the leap. And it's a big leap to leave a full-time job and a regular paycheck, and with a new family, jump off and start a company. So I'm a little nervous.
I can imagine. I mean, I went through similar things, not with the family, but with the stress of questions about starting businesses.
And by the way, we didn't know anything about starting a company. The most I knew was that I had a paper route back when I was a kid. That's the most I knew about business at that time. So
okay, so great question, because there are a lot of people in the audience probably saying, I want to start a business, but where do I learn? I mean, obviously there's more information on the internet these days, and there's a ton of coaches and a ton of experts who probably are not experts. But back then, who would you go to and say, or how'd you learn to build a business?
Well, actually, it turns out you learn a lot from the paper route.
So what did you learn from the paper route? What was the most?
Well, it was like, okay, you have to have customers, you have to sell stuff, you have to collect the money afterwards. I mean, these are like.
And what about the dogs that taste you? I mean,
yeah,
it's similar.
I hadn't thought about the dogs, but you're right. The dogs are important to deal with too. Because it's really dog eat dog
exactly.
out there.
So there's other types of dogs. They might not be four-legged in the business world, but they're.
Well, actually, the good thing is when you start a company, usually it's a new area, and the big players aren't even paying attention to you. They're like, oh, that's interesting, or you're not a threat whatsoever.
Right,
it's only when you start to eat into their business that.
So tell us a little bit about that, because then now you're maturing, you're learning how to build this business, and for a while they're saying, hey, it's irrelevant. CCD is the thing, CMOS, you're still crazy. Right. We like you, Eric. I've heard similar things, but about me that oh, you're a nice guy, Evan. When we started LDV Capital, invest in vision tech companies in 2012, they said, hey, that's cute and niche and science fiction, but good luck, Evan.
Yeah.
It's fun. It's still growing. It's not, it's a community. So That's frustrating. Give me one of the experiences as you're growing up and they're still not this company, they're not accepting you yet, they're not adopting. What was the night, how did you deal with the kind of wake up at 4 a.m. nightmare anxiety of, is this going to work or not?
Yeah. Well, you really just have to kind of ignore that. It's like climbing a steep mountain or something. Don't look down, just kind of focus on what's immediately ahead of you and focus on that is pretty important to do. And there are ups and downs, so there's days that you eat bear and there's days that bear eats you. And you just have to remember that there is this cycle and get through those hard times.
Yeah. It's a big topic. I mean, in collaborating with entrepreneurs all the time and being one, that's one of the biggest struggles is how do you go through the roller coaster life? We're going to talk tomorrow with Amal Sarva, who's founded his 5th company in the roller coaster rides of that. So as you started getting adoption, give us a kind of behind the scenes of those. How did you get Kodak? I mean, was Kodak probably the main one? How long were you talking with Kodak? How many people? And what kind of do you think, triggered the the no to maybe to a yes?
Well, so we did do a contract with Kodak, and I think it was because George Fisher came from Motorola to take over running Kodak, and he understood the importance of the semiconductor business to the future of Kodak. So there was the guys in the grassroots engineers that were very positive and encouraging. And then there was George Fisher at the top, and then there was this middle sandwich, as I understand it, that was really the dead layer. That was just like George couldn't control it from the top, and the grassroots couldn't penetrate it from the bottom, and just basically, as my friend Steve Appleton used to say, former CEO of Micron, it's like the antibodies come out of the woodwork and just like kill the new thing as fast as they can.
Right.
So Kodak suffered from that, and it's too bad. But it was probably the middle layer that was the worst.
Okay, now so go forward a little bit and give me a year kind of. So now when did it start? You mentioned Kodak and others started licensing the technology, and there's probably another tipping point at that company. So tell us about that and what was the realization?
So one thing that really helped a lot was that Toshiba made the step into producing this kind of technology and working on it. And of course, that was one of those the bear eats you kind of days, like, oh my God, Toshiba is like entering our space. And yet
as a competitor, I'm sorry.
As a competitor, absolutely.
Right, as a competitor. So did you start hearing rumors about it? Because that happens in all the companies all the time. Oh, this company, Google or Facebook or a small startup is going to compete with us now.
Yeah, it's, there wasn't a lot of rumors. Suddenly there was a product.
Oh, really?
That they were launching.
They were really stealth for a long time, and all of a sudden we're live.
Yeah.
Boom.
But actually, it had a different effect than we expected, because all of a sudden it was like, oh, if Toshiba is in this business, this must be a serious technology. Right. And as they say, kind of raises all ships, the rising tide. Mm-hmm. And it did for us, and it helped a lot. So, we had a very strong relationship with Intel, for example, in their first web camera. And they were a great company to work with, and until the bear ate us again when Intel decided that they were exiting the consumer electronics business. That was a bad day, bad month.
So how did you recover from that? I mean, were there times in that phase of all companies go through the near-death experiences?
Right.
And I don't want to boil your blood or mine as we start reflecting on our own, those near death. Was there a moment of near death? And how did you get out of that?
Well, there was a retrenchment, and there is nothing more sobering than having to lay people off from your startup company.
And what happened? Was it the competition, or was it took longer than you expected, or what was the reason you had to retrench?
Well, just we had a couple of big customers, and Intel was the largest at that time. So all of a sudden, sales go to zero. Right? They canceled everything. So what do you do with all this capacity? I mean, you just can't keep it going. So we had to rebuild capacity through other channels and working with other companies. And came back. But there was also about the time that we decided that, this thing is going to be big. And looking around our management tables, like, we don't know how to scale this thing. So that was another milestone in the company.
Exactly, I was about to get to that, so it's great. So worrying about scaling, in what regard? Give us a kind of a detail, or some, what was the scale that you needed in order to compete with Toshiba, or needed just to scale your business? What was the major challenge there? Because that then led you to we're going to, tell us about the, acquisition and/or sale and why and to who.
Right, exactly. So, well, you figure out you need a lot more people, like 10 times more people to scale.
And how many did you have at that time?
We were about maybe 120 to 130 people at that time, and it's just like all areas of the company. You need more people. So, and we were in a very specific technology area, so finding people would not be easy. And we're in Pasadena, so we're not even up in Silicon Valley at that time. So we made the decision that maybe we should look to get acquired by a company that was already big and had a lot of the right skill sets. And Micron entered the picture, and we wound up doing an acquisition by Micron.
So that's great. So, but they came into the picture is a very diplomatic way to say it. So, what was the behind the scenes of? Were there options? Was it the right fit because you wanted to work with them? Was it opportunistic? Was it a coffee chat or a whiskey chat that somebody said, well, let's work together. We'll buy you.
Yeah, not that.
What was it?
Yeah, no, there was if you may recall, there was a big recession going on at that time, especially in the semiconductor area. So it was probably one of the worst times to try to sell a semiconductor company. But we tried to talk to all the big guys, Motorola and Intel and Micron, and Steve Appleton was one that was really quite interested.
With a banker or just you trying to hustle and meet them all?
Mostly through a network of people that we know, like 1 degree of separation type of people. So
hustling.
Yeah, it was, one of the many things in retrospect we could have done is probably like used a banker to go do this, but...
Sometimes it makes sense, sometimes it doesn't. I mean, it's the relationships in the end, probably that 1 degree of separation, building those relationships.
Right. And then Micron, we went through a lot of due diligence with Micron, and then some other shiny thing came onto their radar, and they said, we're too busy to do this deal, so we're going to go do something else. And then after some management change, I called up Steve Appleton and said, let's try again. And he said, okay. And then we closed the deal soon after that. So
that's great. Soon after that, it's like hours or days or months or years?
Couple months.
Great.
Yeah.
It takes time.
Yeah.
So congratulations on that. And then you decided, was retiring the goal after that, or what was?
Actually,
you went to another company after that, and then
I stayed with Micron for a year, mostly because this team that I built, this was my baby. It was my technology baby. It was the people, and I didn't want to abandon them. And then it was a very tough year for me. I mean, you can't go from being the big poobah to not being the big poobah. It's especially when the people that are in charge don't know as much about the technology of the field as or the market even as you do. So it was hard, and finally about a year into that, I decided that retirement looked awfully nice. So I went off to New Hampshire and retired.
Pasadena to New Hampshire to the horses and the
yeah.
So skipping forward. You did a couple other kind of entrepreneurial initiatives and consulting stuff, but we're going to skip forward to becoming a professor at Dartmouth, and tell us about kind of what you're focusing on there now and the entrepreneurial initiative, which kind of is great for this audience because we've a bunch of researchers, professors, and people that want to start businesses, and it'll lead into our next step.
Right. Yeah. So I was fortunate to find Dartmouth. It's a great school, and very open to entrepreneurial thinking, by the way. And but I was only going to do it part-time, by the way. I was only going to teach one course and work with one student, and now I have a more than full-time job there.
What happened to retirement?
Because I liked it so much. It was just hard to say no. All these new opportunities came up, and got some great students, and got back into the whole research thing, and
tell the audience about the Quanta research and how it led to the new startup that you're working on.
Yeah, so a friend of mine, Junichi Nakamura, wrote a nice book on DSLR cameras and processing, asked me to write the last chapter on the future of cameras or image sensors.
Right.
And I was thinking, pixels are getting smaller and smaller, and the amount of signal they can carry is getting smaller, and what's kind of the ultimate limit to all this?
Right.
And so I thought, okay, well, what if we made a pixel that was so small it could only hold one electron that's generated by light. So and what would you do? I mean, how would you go about building a camera with that sort of thing? So I worked on it for a while. Actually, I was running a MEMS company as CEO at the time, so nothing to do with this, but I was doing it in my spare time.
Okay.
And
In the same basement? A different basement now?
It's not different. It was actually more like a real company.
Oh, okay.
In Pasadena. So anyway, had this idea and couldn't do much with it at that time, but when I went to Dartmouth, I thought, okay, I'm going to take a look at this. It's like, how can we build this imaging system and with just bits, basically sensitive, a detector that's sensitive to one single photon. Mm-hmm. And a photon is like the smallest particle of light that there is, right? In fact, a 60-watt light bulb puts out a billion photons per second.
Huh.
Okay, so we just want to be sensitive to one photon. Just one. And then we're going to make 1 billion pixels on a chip. So, and it'll be ones and zeros, like a scene out of the Matrix or something like that, right? Mm-hmm. And then we're going to take a new picture every 1/1000th of an image, so 1,000 frames per second imaging. And we're going to wind up then with this XY map of ones and zeros where photons hit it, and then many, many time slices, so it's a giant cube of ones and zeros. And we're going to give that to the computer science community and say, go.
Okay.
So it was pretty far-fetched. Actually, at the time, I didn't think I was going to give it to the computer science community, but decided that was the right thing to do.
Because?
They know a heck of a lot more than I do about creating images from this kind of data.
Okay.
And they're very excited about it, too.
Okay.
So I was like, okay, this is a great problem for university. Like, impossible, right? We're going to detect a single photon, we're going to put 1 billion on there and read it out, and we're not going to, by the way, burn much battery power either. So how do we do all that? But fortunately, I had some great students. One of them's here somewhere, Saleh Masoudian is sitting up there. And another one, JJ Ma. And so Saleh figured out how to do the electronic circuits to use very, very low power. So we could read out 1 billion pixels fast.
Is it now a flashback again where they're saying, no, this is crazy, Eric, you can't do that?
Yeah, it is. Well, actually, you know what happens is that after you do something like the CMOS
they're a little
sensor,
more open to.
Yeah, they're like, I think they might quietly in their brain say he's crazy, but they'll just smile nicely too this time.
So that's a big difference. Before they would just not take your meetings. At least now they'll take your meetings.
Right.
Right.
And then another student worked on the actual detector structure, how to build that semiconductor device, which was a new way to build a pixel. And we wanted to do it using, this is the other challenge, is like, we need to do it using existing commercial fabrication technology with just a few minor tweaks. So, because I want to be able to make
do something revolutionary, but with minor tweaks to the present.
That's right.
Not ambitious at all.
No, not ambitious at all. I have to say that fortunately, Rambus also believed in this dream, so they actually funded our research lab for a number of years. So thank you, Rambus. So. Yeah, we built this chip that's got now had so this is the prototype chip. So it's just got 1 million detectors on it. Each one is sensitive to a single photon. Actually, we have some
walk us through the picture here.
Yeah,
if you put the picture up there on screen, and you're calling this company GigaJot.
That's right.
And so walk us through this infographic.
Yeah, so up there on the top left, you see this is the map of basically ones and zeros. The ones are white and the zeros are black, those dots. That's the raw photon map from a single frame. And of course, if you look, kind of pull it back, you'll see that it's part of a bigger image. And then we're collecting a lot of these slices of ones and zeros over time.
Those are the multiple fast capture,
That's right.
Frame capture here.
By the way, so I should mention that the target is 1 billion pixels at 1,000 frames per second, which is a terabit per second of data.
So that's your tweet, everybody, if anybody cares.
Yeah.
Did you ever get that? What was that again?
Yes, a terabit per second of data. Terabit per second.
So as I mentioned earlier in a couple of our sessions and making introductions, and this, leading into is obviously I knew what we were going to talk about, the concept of our tech infrastructure for the visual tech industry. When this project and many others that might be collaborate together. The tech infrastructure, as we know it today for visual tech, will be nothing like it'll be in years in the future. The question is when and who and how.
Maybe.
Or maybe.
Maybe.
Okay.
Yeah,
I'm a little bit more pessimistically optimistic, and we can keep on going.
Yeah. So anyway, we got to take all this data, and then we create an image from it just by doing local neighborhood processing, and we can control the resolution and the sensitivity by how many pixels we combine in creating each grayscale pixel.
Got it.
And then actually it can also be improved quite a bit. This last image actually, not only did we do all that, but it was improved by an algorithm by Stanley Chan at Purdue. So thank you, Stanley. So we're working already in the computer science community for that.
Great. So go ahead. What were you going to say?
Oh, go ahead.
So what did you learn in your early entrepreneurial experiences that you're going to do differently in this company?
Yeah, I knew you were going to ask me that question. And, well, hopefully I know more. So that's the very first step.
Yeah, I'm sure you do.
Yeah. So I kind of have more of a view of where we're going. And
what's one thing that you learned back then? You're like, God, I'll never do that mistake again.
Yeah.
And have you succeeded in not doing it again is one of the hardest things.
Hard to say if we succeeded.
Well, at this stage in building and putting it together from the early days when you built.
You may not like this answer.
I don't care.
But
it could be the real answer.
Yeah, I'm trying to avoid preferred share stock.
Okay. That's good. I mean, this is what, if you can, that's an option.
So, our strategy is to use federal funding like SBR programs and things like that to fully develop the technology, and then maybe team with strategic partners that have a long-term interest in this, and they become shareholders. The second company I ran, which we didn't talk about, was all VC funded, and let's say it wasn't such a great experience.
I've been through some of those experiences on the entrepreneurial side as well.
So I'd say that's the number one thing I learned. If you can at least avoid dilution before you bring in a lot of venture capital.
But dilution versus preferred shares are very different things.
Yeah, well,
and they're sometimes part of the same, depending on who you raise money from.
Yes.
But reiterating, it's not that I dislike it. I think every company, every entrepreneur, more importantly, should decide what kind of company they want to build. And funding is a means to an end, and there's many different types of investors, as you say, from grants to angels to VCs.
Now, one thing I did learn is that there is value in bringing a lot of capital to the company. Once you reach a critical stage in the technology development, when you really need to start to scale it up, then you really need the cash. And how you go about getting that cash is still a mystery for this particular company.
Sure.
And we'll see what happens.
Great. What's one use case that you're excited for this technology? And give us an idea of when, one of the questions that you get asked a lot, when will that use case start be able to use this technology, roughly?
Well, I think the farthest out use case is like the oldest. It turns out the response of this type of detector, where you have ones and zeros, is just like old-fashioned photographic film. And so there's a lot of pull from cinematographers and photographers to bring this back. Now, will that turn into a big business? I don't know, but to me it's kind of cool to use the future to go back to the past.
Yeah.
But certainly for low-light imaging, you can't do any better than detect a single photon of light.
So I used to photograph with T-Max 3200 speed film and push to 6400 speed film, shoot in black and white with a Nikon F and a Nikon FM, and I loved it. But I also loved the big grain, in those images when I was processing in the darkroom. And so you're saying basically this technology would enable, and I did that because I hated flash and I could photograph in the dark. So with GigaJot, not just for a professional photographer, but anybody in low light conditions, is basically the solution one solution you're trying to address.
Yeah, well, actually, it's the combination of computational imaging with the single photon detection. Because as you know, when you take an image in the dark, there's two types of noise sources. One is the intrinsic noise in the light that comes in, and the other is the readout noise in the electronics. So we've eliminated the readout noise in electronics. We're left with the statistical nature of photons, But it turns out with AI and, or maybe at least just neural nets, not quite full-blown AI, you can create pretty decent images for just seeing a few photons, like that picture I showed from Stanley Chan is part of that work. So that means that if you have an Internet of Things,
Or Internet of Eyes.
or Internet of Eyes, which have eyes, presumably, they're going to be in a lot of places where there's not a lot of light. And being able to generate a image where you can recognize people or things or objects under those kind of crummy conditions where there's motion also going on, I think is going to be very important for this Internet of Eyes in the future. And so being able to combine the super low light detection capability and the ability to combine all that data together in a computational way is going to be very interesting, I think, for this future application. It doesn't have to have 1 billion pixels on the chip. It could just have a few million.
Or a few billion, not.
Yeah.
And so, roughly when?
Well, I think that sort of thing could be ready in just a few years.
Okay.
So kind of excited about that.
That's great.
And there's all kinds of other low light applications. Security.
Okay, I'm sure they'll come up. We've got a couple minutes left. Questions, anybody from the audience? I've got many more questions. Eric, you might have questions for me or the audience, but who has questions? And this is the stage where I kind of say, if you don't ask questions, we don't know how brilliant you are. So the better question you ask, the more we can't wait to meet you in the break and say, that was phenomenal, you're smart. Usually the hands always go up once I say that. It's really amazing, the little inspiration that happens.
Experience.
Yeah, been there before.
So you mentioned super interestingly that Kodak thought it was a chemical company, right? And a lot of this conference is going to get into the blockchain. What do you think is what the chemical equivalent that's going to power or be required for this technology? How can you kind of get into that space, and what do you think about there?
I think very low power AI systems is really what's needed. Right now, AI systems consume a huge amount of energy to do their computation. I don't think it's sustainable. So I think technologies that drive AI systems to lower power are going to be needed, and it may not be electronic, it may be biological. We'll have to see.
Interesting. Questions? Other questions? Anybody else? All right, I'm going to ask a couple more questions. The most important advice, you work with students, you work with researchers, you work with entrepreneurs, and you are a serial entrepreneur. What's the most important advice for those that are starting or want to start commercialize a business? What would you tell them?
Well, I think the number one thing I tell the engineers, at least, is that whatever technology you've got has got to be compelling. Not just a little bit better, not just a small improvement. It really has to change the way we do things, which, by the way, is a huge ecosystem problem, but or it's got to make things so much better, like being able to put a camera in a pill camera and swallow it, something you could never have done with a CCD before. So being sure that your new thing is compelling is really important.
How do you, so everybody has a different perception of what compelling is.
Right.
And how do you define that level of compelling or not?
10 times better.
Than what exists now.
Right. Actually,
or that
you have to be a little careful. You have to look ahead a little bit to make sure that you don't miss
that. So that's what I'm saying.
Yeah.
So what, 10 times, so maybe 20 times from now and 10 times from 5 years from now.
Yeah.
Roughly.
Good rule of thumb.
Right? And so, that makes a lot of sense. Yes, question over here. We're going to get a mic back there, Alan.
Eric, I wonder if you could comment on any observations in tech transfer from your time at JPL to today at Dartmouth.
By the way, it turns out I have this administrative job at Dartmouth, so I'm in charge of all the entrepreneurship programs and the licensing and patent office and all that stuff as associate provost. That's kind of the dark side for faculty, but I'm doing that.
I like the dark side, I think.
Well, a little bit.
Yeah.
It's okay to dabble in the dark side a little bit. Yeah. I borrow your hat for a while.
Sure, absolutely. You can have it. Absolutely.
But I think tech transfer at Caltech was pretty primitive when we did the spinoff. In fact, the whole technology transfer office at Caltech grew up considerably after the the period of Photobit spinoff, and they start doing a lot of things. But we were like #1 out of JPL for that. And it, it was kind of a licensing arrangement that was a normal straight licensing deal. At Dartmouth, we have I would say, a much better approach for faculty startups. We really want to encourage that because that's the way that the knowledge that we develop at a university gets out to benefit society is through tech transfer, and entrepreneurial activity is like the key, the best way to transfer technology, I think. So faculty, in fact, can basically get with just a very small equity stake, basically get exclusive license to their IP that they develop, and go. And we encourage them to do things. And it's like a complete sea change.
Real quick last question. I'm sorry. There's going to be networking. We got to move on to the next step. In the back, over there.
Yeah, so we're going to have terabyte per second, but what about the computation power? How do you think the computation power industry should proceed in order to process so much of data?
Right, so I think there's no doubt that there's going to be vaster amounts of data in the near future. So so certainly there's the normal trends like development of very small devices and things that take less power, but I think it might even be time to take another look at analog things, and I was serious about biological computation too. Why try to recreate a three-dimensional brain with electronics when you could grow one in the lab? Give or take ethical questions and moral questions and all that kind of stuff, which are big questions, by the way.
Yeah, they're big questions. They're important questions. Break things and then fix them. Okay, so we're running out of time. This has been fantastic. I like there's one question I frequently ask serial entrepreneurs and investors because it helps the people building companies in the audience. So there are, good and bad personality traits in people and everywhere. In entrepreneurs, what is your favorite personality trait and your least favorite personality trait in one-word answers? So that personality, what's the best one-word kind of personality that an entrepreneur needs to succeed?
Bullish.
Bullish. What's the least favorite word?
Arrogance.
Great. So this is one of the questions I always love. So bullish, you need to be bullish and attack, and arrogance, is negative. My determination is one that's positive, and selfish, is the other. And so it's a team effort, and I think there's some similarities in both of those. Eric, thank you very much for joining us. Let's give a round of applause. I appreciate it. We'll talk in a little bit. Thank you very much.